graph.
What was the question?
In shown figure, an ideal gas changes its state from state A to C by two paths ABC and AC. Calculate the internal energy of gas at A is 10 joules and the amount of heat supplied to change its state to C through the path AC is 200 joules. Calculate the internal energy at C.
Just 1 minute. Question number 5.
Yes, sir.
This was assignment?
Yes, sir.
In the figure, an ideal gas changes its state from A to C by two different processes. First, along ABC, and next, directly along A to C. So we have to find the path along which work done is least. So you will simply say, let's say for ABC, pressure versus volume. So if you draw a vertical line, so total area inscribed in this process on going from A to C along this path will be about this much. But in case of directly A to C, the total area inscribed will be just this much. Is it clear?
Yes, sir.
So in which do you think will have more amount of area or more amount of work done? For
First.
ABC, okay. It means work done along ABC is greater than work done along AC. So work done along ABC is greater than work done along A to C. Now next, the internal energy of gas at point A is 10 joule, and the amount of heat supplied to change its state to C through path AC is 200 joule. Calculate internal energy at point C. So first we have to calculate work done along this path. Work done along path AC will be area under the graph A to C, and this particular diagram is related, I think it will be trapezium. So half sum of parallel sides, 5 plus 15, and change in its volume, 6 minus 2. So 5 plus 15, 20, divide by 2, 10, multiplied by 4, so it will be 40 joule. Samira, is it clear?
Yes, sir.
This is amount of work according A to C. So according to the formula, heat equals to change in internal energy plus work done. So heat supplied along this path is 200 joule. Change in internal energy we have to calculate plus work done in this process is 40 joule. Work is done on the system or by the system. So you'll say since graph is in clockwise direction, so work will be in positive, that is work done by the system. So on rearranging, change in internal energy will be 200 minus 40, that will be 160 joule. And this change in internal energy will be internal energy at final state minus internal energy at initial state equals to 160. At point A, we have internal energy 10 joule. So internal energy at point C, we have to calculate is 160. So UC is equals to 160 plus 10, that will be 180 joule. Is it clear?
So 170.
Okay, just 1 minute. Okay, any doubt?
No, sir.
In third part, we have to calculate the internal energy of gas at point B is 20 joule. Find heat supplied to go from A to B. Similarly, we may calculate work done along this path. Work done along path A, B, C is simply length times breadth. Length we have 6 minus 2 multiplied by its vertical length, that is from 0 to 15, the total area inscribed in this particular path. So it will be just 15 minus 0. So 15 into 4, 60 joule. According to the formula, dq equals to du plus dw. Just put the values and simplify it according to the above part. You will get your answer. Samira, is it clear?
Yes, sir.
Okay. Arslan, there was a little mistake in your answer. Since in this process, which is taking place abruptly, so we can say delta Q will be 0. That means it will be adiabatic process. And in adiabatic process, temperature and pressure should be directly proportional to each other. So inside tire, it will have larger pressure. On coming to outer atmosphere, pressure will decrease and consequently temperature will decrease. Hence, air will become colder. Is it clear, Aslan? It was second question, but in first question, similarly, since heat supplied is 0, so change in internal energy plus work done will be 0. So if we move this work done towards right side, so change in internal energy will be minus of work done. And since work is done on the system to compress it, so work done during compression will be taken as negative. So this is minus of minus work done. So minus minus become plus. It means change in internal energy is positive. So it means heat or temperature of system will increase. Samira, why I have taken work done to be negative? Is it clear?
So can you please explain?
The question was, when a gas is suddenly compressed, it gets heated up. Why? So only in certain compression, certain expansion, when the process is done very quickly or abruptly, we call it as adiabatic process. And since this is compression, so in compression, work done will be taken as negative. In expansion, work done will be taken as positive. That's why I'm taking work done to be negative. Is it clear?
Yes, sir.
Any more doubt?
No, sir.
The last part we have done in last class is about heat engine, the working mechanism of heat engine. So from this part, we have to calculate net work done during this entire process. Net work done will be work done along path A to B, work done along B to C, C to D, and then work done along D to A. Along path B to C and along path D to A, both is an adiabatic process. So one is in terms of expansion and the other in terms of compression. So both will be equal and opposite. So just cancel out. So we're left with work done along AB and work done along CD. That's it. Work done along AB is in isothermal expansion. So total amount of work equals to total amount of heat supplied during this process. So it will be taken as Q1 in positive sign since it is supplied to the system. And next part, work done along CD, that is isothermal compression. So Q2, and since it is in compression, so heat will be being ejected out from the system, so it will be taken as negative. So net work done during this entire process will be Q1 minus Q2. Samira, is it clear?
Yes, sir.
Now, according to this, we have to calculate efficiency of heat engine. So how to calculate efficiency or working ability or working performance? So efficiency is work done divided by heat absorbed by the system. So work done is Q1 minus Q2. Heat absorbed by the system is Q1. So on solving, you will get 1 minus Q2 divided by Q1. Is it clear? Arslan, any doubt? Okay, just write it down. We have to transform this particular relation in terms of temperature. So first write it down. I'm transforming.
Done, sir.
In terms of temperature, since according to the relation Q2 equals to heat ejected out during compression or during isothermal compression. So it will be equals to amount of work done along C to D. So it will be equals to NR temperature T2 log V final divided by V initial. initially at this point, having P1, V1 and temperature T1, then B, P2, V2, temperature T1, isothermal expansion, then point C, P3, V3 and temperature T2, adiabatic expansion, then at point D, P4, V4 and temperature T2, isothermal compression, and then return back adiabatic compression to A. So work done along C to D will be nRT2, temperature in this process, and change in volume, that is final volume divided by initial volume, so V4 divided by V3. Next, Q1 will be work done along A to B, and it will be nR temperature T1 ln V2 divided by V1. Is it clear?
Yes, sir.
So on dividing, we can write Q2 divided by Q1 equals to nR cancel out. So T2 divided by T1 multiplied by ln V4 divided by V1 whole divided by ln V2 divided by V1. Now, according to sign convention, Q2 is heat being ejected out from the system, so it will be taken as negative. Q1 is heat supplied to the system, so it will be taken as positive. So Q1 will be negative, Q2 will be negative, and Q1 will be positive. Heat supplied to the system will be positive, and heat being ejected out, so it will be negative. I've just used this particular sign convention in this part. Now we have to somehow relate these volumes, so this ln part will get cancelled out. So we're left with Q2 over Q1 equals to T2 over T1. So let me define you how to solve this part. Now for path B to C, that is along adiabatic expansion. So delta Q equals to 0. According to adiabatic process, for temperature and volume, it will be T1 volume to the power gamma minus 1 equals to T2 volume at point C V3 to the power gamma minus 1. I'm just using relationship between temperature and volume for this adiabatic process. So on rearranging, T1 divided by T2 equals to V3 divided by V2 whole to the power gamma minus 1. So if you move this exponential to other side, so you'll get T2 divided by T1, and exponential or moving to other side, get reciprocal. So you're left with V2 divided by V1, V2 equals to this part. Samira, is it clear?
So why T2 is coming at the numerator?
Just 1 minute. Now it's correct?
Yes.
Okay. Similarly, for path D to A, again, we have adiabatic process or adiabatic compression. So at point D, we have temperature T2 and volume V4 to the power gamma minus 1. And at point A, temperature is T1, volume is V1 to the power gamma minus 1. So move this T2 to right side and V1 to left side. So you will get V1, V4 to the power gamma minus 1 equals to T1 over T2. Move this exponential to other side. So V4 divided by V1 equals to T1 divided by T2 whole to the power 1 by gamma minus 1. Now just relate these two expressions. We have same quantity of temperature in both terms. So when we can equate them, so we can say V3 divided by V2 must equals to V4 divided by V1. Is it clear?
Yes, sir.
And move this V2 to right side and V4 to left side. So you may write V3 divided by V4 equals to V2 divided by V1. First, write it down to this part.
Done, sir.
Aslan done. Now we can say, according to the above result, minus of Q2 divided by Q1 equals to T2 divided by T1 multiplied by ln V4 divided by V3 whole divided by ln V2 divided by V1. There is a property of log. If you have minus of ln x divided by y, this minus will get this exponential part of this x. So you may write x divided by y to the power minus 1. It means exponential will get multiplied with coefficient in terms of log. Now this exponential will be able to transform this fraction. So you may write this expression as y by x. Similarly, we may write this V4 divided by V3 as minus of T2 ln V3 divided by V4 whole divided by T1 ln, in place of V2 divided by V1, we may write using this as V3 divided by V4. Samira, is it clear?
Yes, sir, clear.
So ln V3 divided by V4 will get cancelled out in both terms, and minus of Q2 divided by Q1. So this minus and this minus will also cancel out. So you're left with Q2 divided by Q1 equals to T2 divided by T1. Therefore, efficiency, which was 1 minus Q2 over Q1, now becomes 1 minus T2 over T1. So you'll be asked to calculate or to define efficiency in terms of temperature. So you have to do this entire process. Arslan, any doubt? Okay, just write it down. Samara, done?
1 minute. Done, sir.
Okay. Now, according to this relation, you will be asked, is it possible to design a heat engine having efficiency 1 or 100%? So you'll say for that part, if efficiency have to become 1, so in this part, T2 will have to become 0 or simply 0 Kelvin. So in that part, this entire fraction will become 0. So eta equals to Q1. So if T2 have to become 0 Kelvin, that is at 0 Kelvin, there will be no existence of matter. So it can't be possible. Is it clear?
Yes, sir.
So you can say for efficiency of heat engine to become 1 unity or 100%, T2 must be 0 Kelvin. But at 0 Kelvin or absolute 0, there will be no existence of matter. Hence, it can't be possible. Arslan, any doubt? Shravya, just 1 minute.
Done, sir.
Okay. Shravya, you may take a screenshot. From this part.
Done, sir. Done, sir. Done, sir.
Okay. Now, according to the last formula, you will be asked to calculate some numerical. First, find efficiency of heat engine working between ice point and steam point. Just 1 minute, I'm giving you some hint how to calculate. We have first temperature, ice point, and second temperature, steam point. So the smaller temperature will behave as sink and the higher temperature will behave as source. So T1 is a steam point. So convert into Kelvin. So 273 plus 100 becomes 373 Kelvin. And T2, lower temperature, that is ice point, 273 plus 0 degrees Celsius. So it will be 273 Kelvin. Now use the formula and try to find efficiency. Try to solve. Shravya, this is the formula to calculate. Eta is efficiency of heat engine, which is equals to 1 minus T2 by T1. T2 is temperature of sink and T1 is temperature of source.
Okay,
Try
sir.
to good, Shravya. Samira, you got any answer?
Yes, I'm sending.
Arslan, just send me your answer. Good, Samira. According to the formula, eta equals to 1 minus T2 over T1. So 1 minus T2 we have 273 divided by T1, 373. So on taking LCM, you may write 100 divided by 373. So on solving this fraction, you will get 0.268 or simply 0.27. In terms of percentage, it will be 27%. Now, if a heat engine working between 27 degrees Celsius and 127 degrees Celsius absorbs 2 kilojoule from source. Find first efficiency, second amount of work, and third heat ejected out. First, convert temperature into Kelvin, then try to find efficiency and rest of the part. Yes, Shravya. Shravya, just take your calculation. Eta equals to 1 minus T2 over T1. So the
Should
lower
have
temperature,
taken T1 as 300. I should have taken T1 as 400. So that's why I'm getting negative answer.
T2 will be lesser and T1 will be higher. Okay.
Yes, I interchanged both of them.
Okay. Okay. T2 will be lower and T1 will be higher. So T1 will be 127 plus 273, that will be 400 Kelvin. And T2 will be 27 plus 273, that is 300 Kelvin. Good, Samara. Good, Shravya. We have 2 kilojoule heat absorbed from source. That is Q1, we have 2000 joule. So you may write efficiency is equals to work done by heat absorbed from the source. Using this relation, you will be able to calculate work done. And then work done equals to Q1 minus Q2. From this part, you will get the value of Q2. Good, Shravya. Good, Shravya. Samira, just check your calculation. Eta is 1 minus T2 over T1. T2 we have 300 Kelvin. T1 we have 400 Kelvin. So this and this will cancel out. So on taking LCM, 4 minus 3 will be 1 or 0.25 or simply 25%. Now putting this in this part, work done divided by heat absorbed 2000. So work done will be equals to 2000 divided by 4, that is 500 joule. If you put in this part, 500 equals to 2000 minus Q2. So Q2 equals to 2000 minus 500, that will be 1500 joules. Good, Samira. Arslan, is it clear? Okay. Now, next is demerit or simply limitation of first law. You will say in first law, it simply defines the flow of heat would be unidirectional, that is from higher temperature to lower temperature only, and reverse was not possible. So you'll say first law defines unidirectional flow of heat, that is from higher temperature to lower temperature body, and reverse is not possible. Then we define second law, for which we have two different statements. One is Kelvin-Planck statement, and the next is Clausius statement. So next is second law of thermodynamics. First is Kelvin-Planck statement, and second is Clausius statement. In first part, Kelvin-Planck statement state, suppose we have source this is working tool. Let's state this particular, or in this part, heat is being absorbed, that is Q1, and this entire it get completely converted into work done without any loss of energy into surrounding. So in this part, efficiency of heat engine will become 1 or unity, and it will be not possible. So it state there will be no process possible whose sole result is absorption of heat from higher temperature body and complete conversion of heat into work done without any loss of energy. This will not be possible. Samira, is it clear?
So can you repeat?
In this part state, no process is possible whose sole result is absorption of heat from this source or from higher body and complete conversion of heat into work done, that is mechanical energy, without any loss of energy into surrounding. So for this part, efficiency will be equals to work done by heat absorbed, and since both are equal, so it will become unity, and above I defined you, efficiency of heat engine can never equals to 1. So this entire process will not be possible. Is it clear?
Yes, sir.
The next part is Clausius statement. Says, let's say this is higher temperature body, and this is lower temperature body. In between working tool. it says it absorbs heat from some lower temperature body, and complete conversion of heat or transfer of heat towards higher temperature body. So this will also not be possible. So it says no process is possible whose sole result is absorption of heat from lower temperature body and transfer it towards higher temperature body without any external agency or without any help of external energy. So this will not be possible. Similarly, suppose, let's say this is any object which is placed over any surface like this. So is it possible to go this particular object without any external agency from this point to some higher level? So you'll say no, it won't be possible, since you must have to do some external work against gravitational force of attraction to move it from lower surface, that is from lower gravitational potential energy, to some high gravitational potential energy. Is it clear?
Yes, sir.
Yes.
Okay. So let me define you these two different statements. In first part says no process is possible whose sole result is absorption of heat from source and complete conversion into work, that is mechanical energy, without any loss in surrounding. So this will not be possible. Similarly, according to Clause's statement says no process is possible whose sole result is absorption of heat from lower temperature body and transfer it to higher temperature body without any external agency. So this will also not be possible. Just write it down.
Done, sir.
Shravya, any doubt?
No, sir.
You have written?
Yes, sir.
Okay. So from this part, we can conclude there should be external agency required to move heat from lower temperature body to higher temperature body, or you'll say no heat can transfer from lower temperature body to higher temperature body until external work is done on the system. So on the basis of this part, may define two different devices or engine. First is refrigerator, and second one is heat pump. In first part, case of refrigerator, this is cabin or compartment of fridge that is called a region of interest, for which we have to cool it down. So this is a region of interest, which is initially lower temperature. So it absorbs small amount of heat by adding work from compressor. It ejects large amount of heat into surrounding. That is at some higher temperature. So in this part, to move heat from lower temperature body, that is cabin or the compartment of fridge, to higher temperature body, that is outer surrounding, we must have to do some external work by compressor. Is it clear?
Yes, sir.
Similarly, in case of heat pump, it will be used to heat the room, which is based on this particular thermodynamical system. So in this part, this is surrounding at some lower temperature T2, from which it absorbs small amount of heat, and by adding work from compressor, it eject or donate Q1 amount of heat into room to warm it. So we can call it region of interest. So both are doing the same work, but the region of interest is different for different part. Hence, their efficiency or working performance will be different. So let me define you these two different processes. In first part, in case of refrigerator, it extracts heat from cabin or compartment, that is region of interest, to cool it down by adding work from compressor, it ejects heat into surrounding at higher temperature. So working performance related to this part, working performance denoted by alpha. So we can say for this, refrigerator has to cool it down the temperature of cabin. So how much energy or heat it must have extracted to the total energy supplied to it through compressor by the help of electricity. So it will be termed as heat absorbed from cabin to the work done by compressor. So alpha equals to heat absorbed as Q2 divided by work done Q1 minus Q2. So if you convert this in terms of temperature, it will be T2 divided by T1 minus T2. Shravya, is it clear?
Yes, sir.
Similarly, we may define for heat pump, it absorbs heat from surrounding at lower temperature by adding work of compressor it donates large amount of heat into room to warm it. So working performance denoted by beta. So for this heat pump, it has to warm that room. So how much heat it donated into room to the total work done by the compressor. So heat donated divided by work done by compressor. So beta equals to heat donated is Q1, work done is Q1 minus Q2, or in terms of temperature, it will be T1 by T1 minus T2. Now we have three different engine. First one, heat engine, second one, fridge, and third one is heat pump. So let me define the efficiency of all of them together. Beta equals to alpha plus 1, which is equals to 1 by beta. Samaira, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Sir, please scroll down. Done, sir.
Just 2 minutes, I'm coming back. Okay, Arslan, done?
So why are we adding 1 to alpha?
Okay, in relation of beta equals to alpha plus 1. Samara?
Yes, sir, yes, sir.
Okay, let me define you according to above relation. As alpha equals to Q2 divided by Q1 minus Q2, okay? And beta equals to Q1 divided by Q1 minus Q2. Is it clear? So let me subtract these two parts, beta minus alpha. Beta we have Q1 minus Q2 minus alpha we have Q2 divided by Q1 minus Q2. Is it clear?
Yes, sir.
Now take out LCM Q1 and Q2. So in numerator, you're left with Q1 minus Q2. Is it clear?
Yes, sir.
Now we have same quantity in both numerator and denominator. So on cancelling out, we're left with just 1 beta minus alpha. So move this alpha to right side. So beta will equals to alpha plus 1. Is it clear?
Yes, sir, clear.
Similarly, we may define as eta. Eta equals to net work done, that is Q1 minus Q2, divided by heat absorbed. And beta we have heat ejected or heat donated divided by total work done. Is it just reciprocal of one another?
Yes.
That's why beta equals to 1 over eta. Now, related to this entire term, you will be asked a theoretical question. What will happen to the temperature of room if door of fridge is kept open. Suppose you have any isolated room like this, in which there is a fridge and whose door is kept open. So what will happen to the temperature of room? Will it increase or decrease? Just think. Samira, will the temperature increase or decrease?
Decrease.
Okay, let me define it. It will increase. Okay. If you open the door of fridge, so this compartment and this entire room will become common system. Is it clear?
Yes, sir.
So fridge has to absorb heat from that cabin. Now it had become the entire room. So it absorbs small amount of heat from this entire room, and by adding work of compressor, it ejects large amount of heat into same room. So on each cycle, the work done by compressor will cause us to increase the temperature of this entire system or entire room. Hence, temperature of room gradually increases. Shravya, is it clear?
Yes, sir.
So from this part, we can say, if door of fridge is kept open, so cabin and room will become common system. So it absorbs small amount of heat Q2 from room by adding work of compressor. It ejects large amount of heat into same room. Hence, temperature will increases. Samira, is it clear?
Yes, sir. Clear.
Now, question is, then why we use heat pump? We can use fridge in both season, like in summer, keep the door to be closed, then it will act as cooling agent, and in winter, keep the door to be open, then it will act as heating agent. So why we use heat pump instead of this fridge? So let me define you its working ability and performance. Since working performance of heat engine, heat pump is greater than fridge. So heat pump will act or will do more efficient as compared to fridge. Hence, we will use heat pump as compared to fridge for heating element. Is it clear?
Yes, sir.
Okay, just write it down. This is the last part of this thermodynamics. We have just finished it.
Done, sir.
Arslan, any doubt? Okay. Shravya, done?
Yes, sir.
Okay. Let's start new chapter, Kinetic Theory of Gas. In this part, we have to define three main processes. First is pressure exerted by gas. Second is kinetic energy due to temperature. And third is law of equipartition of energy, and on the basis of which to define mean free path. So let's start with property of ideal gas. Property of ideal gas. In last chapter, I have differentiated between real gas and ideal gas. So in that part, I have told you, if there is no interaction between particle of gas, then it will behave as ideal gas. So first property will be, there is no interaction between particle of gas. Next, particle will move with same velocity along its all direction. So it will have same velocity along all coordinate. That means velocity along x-axis, y-axis, and z-axis will be same. Now, on the basis of which, let me define property. So we can write in vector form v along x-axis I cap, v along y-axis j cap, and v along z-axis k cap. So taking modulus or magnitude of this particular velocity, it will be equals to vx squared, vy squared, and vz squared. Since these all are equal to one another, so we can write 3 times of vx squared root under. Is it clear?
Yes, sir.
Now on squaring both sides, we may write vx squared equals to 1 by 3 v bar squared. So this particular term is also called square mean velocity of gas. Now next is, these gaseous particles behave as perfectly rigid sphere, so it always make elastic collision with neighboring particle or wall of container. So they will behave as rigid sphere makes elastic collision with other particle as well as wall of container. First, write it down to this part.
Done, sir.
Arslan, done? Now, using this property, we have to first define pressure exerted by gas. And in your final exam, you will be asked to derive this expression. So first is pressure exerted by ideal gas x-axis, y-axis, and z-axis. Consider a cubical vessel having side L containing n gaseous particle each of mass small m. So let's say there is a particle at this point which is going along this way having velocity Vx. So on collision with this wall may get deflected along this direction. And since this particular collision is elastic, so there will be no change in its velocity on collision. So due to this part, first we have to calculate change in linear momentum. Change in linear momentum during this collision. So delta P is P final minus P initial. So particle is finally going towards positive x-axis. So mass times velocity along positive x-axis minus, initially it was going along negative x-axis. So minus of mvx. So minus and minus will become plus. So change in linear momentum during this process will be 2 times of mvx. Samira, is it clear?
So can you explain that MVX minus minus 1?
Okay. This particular, each particle having mass m and moving with velocity vx, so it will have linear momentum mass times velocity. Initially, it is going along negative x-axis, so momentum will be minus of mvx, and on collision, its direction get deflected towards positive x-axis, so final momentum will become plus mvx. Is it clear?
Yes, sir.
So I've just put the value of P final to be positive mvx and initial momentum to be minus of mvx. So this minus and this minus will become plus. So it will become 2 times of mvx. Is it clear now?
Yes, sir, clear.
Now, for this collision, this particle has to travel from one side to the other and get returned back. So time taken for this entire process is distance divided by velocity. Distance it has traveled 2 times of L divided by velocity Vx. Now we have change in linear momentum and we have time taken. So according to second law, we can write force equals to a rate of change of linear momentum. So force exerted is equals to change in linear momentum by time taken. So it will be 2 times of mvx divided by time taken, 2 times of L divided by Vx. 2 and 2 will cancel out. So you're left with mvx squared divided by L.
So for time taken, we are using velocity is equal to distance upon time. That formula.
Yeah.
Okay, sir.
But this force being exerted by single particle. So if you have to calculate total amount of force exerted, so you must have to multiply it by n. So for whole particle, that is n particle, force will be equals to n times m into Vx squared divided by L. Now, pressure is force exerted per unit area. So these all particles are hitting or falling on the wall of container that is in square in shape. So pressure will be force exerted over area of impact. Force we have n number of particles each having mass small m, velocity Vx squared divided by length, and area of wall will be L squared. So n number of particles each having mass m becomes total mass. L into L square becomes L cube, and Vx, that is 1 by 3 of V bar square according to the above relation. Now this particular quantity is nothing but mass divided by volume, so it may be written as density. So pressure equals to 1 by 3 rho times V bar square. Samaira, is it clear?
Yes, sir, clear.
Shravya, any doubt?
No, sir, no doubt.
Okay, just write it down.
Done, sir.
So could you scroll down? Done, sir.
Arslan, done? Okay. If 10 to the power 20 particle fall on wall of container at 60° with horizontal at 1 kilometer per second, if mass of each particle is 2 into 10 to the power minus 25 kg, find change in linear momentum. Just 1 minute. Let me give you some hint related to this part. Suppose we have wall of container this and normal to it is this, on which particles are falling at this and get deflected along this since collision is elastic. So it will have momentum along this direction, mv, and then again get reflected at same momentum, mv, at inclination theta, theta. So if you break the component of this particular part, according to resolution of vector, we have mv along this direction having theta. So it will have component along this direction and along this direction. It will be mv times cos theta and it will be mv times sine theta. On getting reflected back, along this direction, having same inclination theta, mv, momentum along this direction will be mv cos theta, and momentum along this direction will be mv sine theta. So if you want to calculate change in linear momentum along y-axis, since having both momentum along same direction, so it will give you 0. Now, change in linear momentum along x-axis will be P final minus P initial. Final momentum is towards positive x-axis, so it will be taken as positive. And initial momentum we have along negative x-axis, so minus of mv cos theta. This minus will become positive. So in total, have 2 times of mv cos theta as change in linear momentum during this entire process. And that due to this particular change in momentum, it will exert pressure or force normally on the wall of container. Is it clear?
Yes, sir.
In this part, I have just calculated for one particle. So if you have to calculate for n number of particles, just multiply it by n. Just put the values and simplify it. Convert velocity into meter per second by multiplying it by 1000. The rest of all other term is in SI unit. For velocity 1 kilometer per second, just write it as 1000 meter per second or 10 to the power 3 meter per second. So Myra, just check the exponential. We have 2. Mass of particle is 2 into 10 to the power minus 25. And velocity we have 10 to the power 3. Cos 60 is 1 by 2. And number of particles we have 10 to the power plus 20. This 2 and this 2 will cancel out. So you're left with 2 into 10 to the power minus 25 into 10 to the power 3 plus 20 plus 23. So on solving, you will get 2 into 10 to the power minus 2 kg meter per second. Smira, is it clear?
Yes, sir.
Okay. Shravya, you got the same answer?
Yes, sir. I just got disconnected.
Okay, no problem. Now, related to this expression for pressure, we may define thermal kinetic energy. So next is thermal kinetic energy as pressure equals to 1 by 3 rho V bar squared So we may write 1 by 3 density as mass divided by volume V bar square. So move this volume to left side and 3 to left side. So you'll get 3 times PV is equals to m times V square. Now kinetic energy is nothing but half mv square. So just multiply this expression by half and similarly half along this way. So this particular quantity will become kinetic energy and it is equals to 3 by 2 times P into. Now we have to convert this expression in terms of temperature. So kinetic energy equals to 3 divided by 2. PV according to ideal gas equation is equals to nRT. So instead of PV, just try nRT. Now, number of moles equals to given mass by molar mass, which is also equals to number of particles over Avogadro number or volume divided by 22.4 liter. So I'm using this expression for number of moles, second formula, that is in terms of number of particles. So you may write 3 by 2 Na, number of moles is number of particles divided by Avogadro number times R into T. Now move this N to left side. So kinetic energy divided by number of particles is equals to 3 by 2 R by Na multiplied by T. Then we introduce another constant Kb, which is equals to R by Na. R is universal gas constant, which is equals to 8.314. Na is Avogadro's number, 6.022 into 10 to the power 23. On solving, you get 1.38 into 10 to the power minus 23 joule per Kelvin, and which is equals to Kb, that is Boltzmann constant. In left-hand side, we have kinetic energy divided by number of particles. So we may write this expression as average kinetic energy, which may be written as kinetic energy to the power bar, which is also termed as average kinetic energy, is equals to 3 by 2 R by Na is Boltzmann constant times T. So this is your final expression of kinetic energy in terms of temperature, since Kb, Boltzmann constant, is constant. Samaira, is it clear?
Yes, sir, clear.
Shravya, any doubt?
No, sir, no doubt.
Okay, just write it down.
Done, sir.
Done, sir.
Okay, let's stop here for today. In next class, I will define the last part of this particular chapter.